Our next speaker is Christian Decker, and he's always talking about L2. So maybe L2 fixes this, right? So give us an L2 fixes this meme. But this time, for once, he's not speaking about L2. He's speaking of channels, flows, and icebergs. So let's put your hands together and welcome Christian.
Thank you. Thank you. So, good morning. Who's disappointed that I'm not going to talk about L2? I see. Oh. Okay. We can talk offline then, and I'll bore you some more with the details. So today I'm going to talk about measurements I did in the Lightning Network. And why am I doing measurements in the Lightning Network? Well, first of all, I wanted to mix it up a bit and not talk about L2 again, obviously. The second one is that apparently I'm an old pony that can do very few tricks, and measurements is exactly what got me started doing my PhD. I measured how decentralized the network in Bitcoin is, and that was basically the basis for an entire PhD, so hopefully this will inspire you to do some academic research as well. And on the other side, we also need to have some ground truth, some real numbers to put behind and drive our development when we further develop Lightning. And this is sort of my attempt to give you this basis point of what we can improve and what we can achieve over time. So what I did is I went out, looked at a few aspects of the Lightning Network, and I'm here to report on the results. These results are by no means complete, but they should serve as a jump-off point for you to do your own research and to sort of look at data that's presented to you and try to figure out if that's really true or whether you should do your own research. Okay, I structured this in three broad topics. The first one is going to be the surface layer, or what can we get from gossip in the network itself. So gossip is basically the nodes chatting among themselves, what channels exist, what nodes exist, what are the parameters of the channels. And this is done basically to allow you, like Fabrice mentioned before, to compute a route to get from you to your destination or from anywhere to anywhere else, actually. So what we do is we basically take a node and dump its view of the network topology, and we look at it. And these are probably the numbers that you already saw in tens of thousands of publications already. This is the easy numbers to get at, and this is basically what everybody's quoting. So since the inception of the Lightning Network, we've had a rapid and sort of steady-ish grow with some bumps in the middle. And since these are the numbers that are sort of always mentioned, I'll just rattle them off. There's 4,400 nodes active at the time I was measuring. That was 2 days ago. 829 of them are publicly reachable, meaning that they accept incoming connections through Tor, through IPv4, IPv6, and a total of 27,394 channels. Now, these numbers change all the time, so take it that that's basically the snapshot I had available when I was measuring, and a total capacity of over 800 bitcoins. So I'm expecting to see a few puzzled faces in here. Didn't I read about 10,000 channels and finally making it to a 10K network? It turns out that the network view that you have of the network is highly dependent on how you measure it. So the 10,000 node number usually comes from 1ML, and they tend to not clean up nodes and channels that have been defunct for a while. So this is basically what C-Lightning sees by cleaning up every channels that have not been active for the last 2 weeks. And this is basically what your routing decisions will depend upon. It's also worth mentioning that this is only the public part of the network. There is a large part of the network that is simply not announced. Those might be mobile nodes, nodes that do not expect to be online for routing purposes later on. So there's little point in them being announced to the wider network because, well, you will not be able to use them. More on that later. Okay, this is boring part over. Let's get to the interesting part. let's actually test the functionality. And this is a bit more involved because it actually involves setting up a node and performing some payments in the network. And the way we do this is by performing probes. A probe basically is I take a dump of the network, basically extract all of the node IDs in the network. Then I iterate through these node IDs and try to send them a payment. Easy, right? Well, there's one issue though, which plays in our favor, namely I don't have an invoice. Then again, I don't want to send people actual money, I just want to see if I can reach them. So what we do is I pick a destination, I randomly generate a payment hash, so that basically means that this payment will never ever be able to complete because it doesn't match an invoice on the recipient side. I compute a route to that destination, and then I initiate the payment. Now this payment will fail because, well, it hopefully fails, otherwise we do have bigger issues like hashing being broken. Once the failure comes back, we look at the failure and then determine what has failed in the network. The failure might be some intermediate channel being out of capacity, some intermediate channel being offline, some intermediate channel being dead, or one of the nodes being dead, or something else going wrong. There's lots of failure cases, and we have a bit of a discussion on a blog post that we published describing this probing mechanism. Now, we did that for all the nodes in the network, all 4,400 nodes. And you can probably see that this is kind of a worst case scenario, right? I am an endpoint and I want to send to every other endpoint in the room a payment. So I'm just trying to prepare you mentally for the bad news that are to come, so yeah. But since most of us are techies, thought I might just show some code as well. Just to show how easy it is in C-Lightning to create a plugin that does a probe. So this is basically the bullet list we had before in code. And it's really like 15 lines of code. And this is even pretty printed. So like I said before, the next slide contains results, and I don't want anybody to have a heart attack when I show them. So be prepared, there's going to be a lot of red here. But I have good excuses for them. So this is basically the first result that is interesting here. We pick a destination, we try a probe once, and then we look at this failure. So this is one attempt, and we see that there is sort of a lot of red. So why? The majority of that, you see the inner circle is mostly covered by the darker red. That is a failure to compute a route from us to the destination. Now, why might that be? Well, because some channel on the path was disabled, and we do broadcast channel state on the Lightning Network so that we don't even attempt those channels if we try to perform a payment. And these 48% were basically us being unable to reach that node in any possible way. And this was a bit disconcerting. So we went out and actually hacked C-Lightning to return routes anyway, and it turns out, yes, that is accurate. Now, I don't want you to be scared of this result, because let's see, how many people are running a Lightning node? How many of those nodes are offline right now? Okay, you're still the most enthusiastic crowd about this stuff. So it's very likely that these are nodes that are running on someone's laptop, on someone's phone, and they simply went to sleep. So I expect this chart to have a diurnal pattern for people going to work, turning on their machines, turning it off again, and a weekly pattern, people going into the weekend and turning off their machines. So yes, we will see how this evolves over time. So I'm planning to do these measurements over and over again. But yeah, that's not the nicest graph, which is why we are going to ignore that part of the graph, because if we can't reach it, there's nothing more to learn about that. we see that there's also a big green part. That's basically the first payment attempt goes through, and we are able to perform the payment without any further attempt. Everything went good, perfect. The yellow part on the left-hand side tells us, yeah, this failed, but it's not final. We still have other routes we can try. So let's try a new route and see what comes out. Okay. Now, for the rest of this, I will just ignore the red part because, well, there's little to be learned from there. But if we clean up that red part, we get a 66% success rate on the first try. Now, that's encouraging. So for 66% of the nodes that we could reach, that we could perform a payment, we will succeed in the first attempt. And given my focus on the first attempt, you might have guessed it, we're just going to retry until we succeed. So on the right-hand side, we have the same plot, but with us retrying over and over again until we reach one of the final states being, okay, the payment succeeded, or we ran out of routes we could try. So the improvement is rather nice. We still have a tiny sliver that is yellow. That is mostly because I stopped at 25 attempts because, well, you have to stop somewhere. Our failure rate now is 20%, which is okay in my book. And you notice that we actually have part of the unable to find route again. That's simply because when we retry, eventually we run out of routes we can try. So that's the reason for that. But we get an 80% success rate. Remember also that I mentioned that this is the worst case. This is us making payments from some random node to some other random node in the network. So if we have an economic node, a business, like Jamison said before, they are likely to be much more connected, to have a higher uptime, and therefore this is a lower bound on what we can expect payments to succeed or not. Okay. Now, these are numbers that do not have any timing information in them just yet, so I also looked at the time until success, or time until completion in this case. On the left-hand side, we have the number of attempts until we actually get to a final state, and like I said, about 66% of them will succeed in the first attempt, and we have a 90th percentile of 4 attempts. So after 4 attempts, we will have succeeded in 90% of the cases, and only in 10% of the cases we will have to perform more attempts. On the right-hand side, we have the same numbers, but in wall clock time. So each attempt takes a bit of time, and the more attempts I do, the longer it takes for my payment to complete. Now, it's kind of bad if I order a coffee, we're using Lightning, expecting it to be quick, and it's still slower than my Bitcoin payment would have been on chain. But luckily, that's not the case. So the plot on the right-hand side shows you that we have a 90th percentile of 30 seconds, which is by no means optimal. So 90% of the payments go through in 30 seconds. And the disappointing part here is that, well, we have a 95th percentile of almost 3 minutes. So in 5% of the times, you actually have to stick around for 3 minutes plus for your payment to complete. The positive side here is that this is a baseline. This is the network as it is today, and this is what we are going to improve on going forward. And these numbers will guide us towards making better decisions. One example of an improvement in this case would, for example, be instead of having them have a testing path sequentially, we might be able to actually probe in parallel for working routes, and then have the probes race against the first attempt. And once if that fails, we have a number of options we can actually try. So there's already ways we can reduce this massively in very little time. And now for the boogeyman in the room. Of course, by performing lots of payments, I also had a few stuck payments. Fabrice mentioned before that stuck payments are really the bane of the Lightning Network because they are really, really bad. Luckily, it turns out they're not that often. So stuck payment, as I define it here, is basically a payment that I initiated, but somewhere along the path, one of the nodes just died on me. So I don't know whether I crossed that gap that this dying node created and this payment will eventually complete, or whether the payment is stuck in front of it and it will never complete, and I basically could retry directly. The reason I cannot retry right away is that the payment might still go through, and in that case I would have paid twice, which is kind of not what I want. But it turns out that out of the 8,000 probes that I sent out doing this test, only 14 got stuck. So this is a stuck rate of 0.19%, and in reality it was even a bit better because I just simply stopped waiting for them once my test run was over. It turns out that 2 more completed after my run completed, and we only really got 12 stuck payments. So that's quite a nice number to have, but we can still improve it, and we do have a few proposals on the table for stuckless payments that would allow you to basically abandon one attempt and retry immediately without incurring the risk of paying twice. Okay, so this is basically that this was the surface. Then we looked into the functional testing of the network, and now for the submerged part of the network. I mentioned before that when gossiping, we do exchange information about channels and nodes that are in the network. That's only partially true. There are nodes that opt out of announcing this information because they want to stay private, because they don't believe that they can contribute to the routing of payments. And so we wanted to take a look at the invisible part of the network. How do we do that? Well, basically we look at the footprint that a Lightning channel leaves on the blockchain itself. And we have a few heuristics that work there. So the first heuristic is that the funding output script is unique. Basically, every time that we open a channel, we create new Bitcoin keys, and both endpoint Bitcoin keys get combined into a new output script, and so this script may never be repeated. A closing transaction only ever has one single input. That is because, well, it's spending the funding output of the channel. Unilateral closes may have non-final sequence numbers. We'll ignore that for now, but it's useful to determine whether a close was cooperative or uncooperative, which is an interesting metric that I haven't looked into just now. The funding transaction only ever has at most 2 outputs. Well, it's the funding output and change. It turns out that this is no longer true since we merged one of the pull requests on C Lightning, because now we can combine or coin join multiple channel opens. So this heuristic will have to be dropped in the future, probably. And finally, only one of the funding outputs is a P2WSH, because the other one is basically paying back to a private key and not to a script. And yes. So we trawled through the blockchain from the time SegWit was activated up until I think Wednesday, and it turns out that that we have 195,000 outputs that would match these heuristics, and by comparing that with the historic gossip in the network, which I've been collecting since we started this whole experiment, it turns out that out of those 195,000, 135,000 were gossiped about. So we only have about 60,000 channels that are not part of the public network. But this is likely to grow once people start creating more private wallets and basically stop announcing themselves to the network as a whole. So the subsurface part of the iceberg is not very big, but hopefully it will grow. And that's basically my numbers. In conclusion, I hope I could give you some idea of what the network looks like, about the directions we should go into to develop further, and maybe there's one PhD candidate that wants to look into this. It's an amazing topic to work on, and I can only suggest you take a look for yourself. Thank you.